So we left off with component form of a vector, which is our pointing bracket notation here that says from the initial point of the vector, wherever that happens to be on our page, we're going to move left 3 units and down 4 units and would be to the terminal point. Now, maybe I wanted to get out my tape measure and I wanted to measure how long this vector is. And so we said finding the length is the same as finding the magnitude. And that's designated with double bars around your vector. A magnitude is the length. It's kind of like absolute values, only there's 2 of the bars. Now we know our distance formula from college algebra that says a squared plus b squared equals c squared, and we snapshot that into our distance formula. So I know from my initial point I've moved 3 steps to the left and 4 steps down. So our magnitude of a vector is going to be the x component squared plus the y component squared, the square root of that. So in our case, if we square -3, we get 9, and we square -4, we get 16, and we know the square root of 25 to be 5. So the magnitude of our vector v, meaning the length of any of these directed line segments up here, that length is 5. That magnitude is 5 for all of them. When I talk about a unit vector, and unit vectors are something that come up quite a bit. If I want a unit, whoa, sorry, my eyes went away for just a moment. If I want a unit vector, just like a unit circle is a circle of radius 1, a unit vector is one of length 1 or magnitude 1. So on the last page, my vector u looked like -3, -4. And we said the magnitude of that vector was 5. The magnitude of it was 5. So maybe I want to point in the same direction. I want to have a vector that points in the same direction, but I only want it to be 1 unit long. Okay. So I need it to only be 1 unit long and point in the exact same direction. I don't know that I got that exactly 1 unit long, but hopefully I'm sort of close. What we do is if we take this vector of length 5 and we keep it in this pointed in the same direction but divide it by 5, then we will have a unit vector pointing in that same direction. Meaning if we learn how to write on this wonky board, okay. If we divide everything by 5, we would get a vector that still goes left 3 units and down 4 units. But when we divide it by 5, then in the end, our magnitude of v is going to be, we'll make sure that we didn't mess anything up. One. So it's still going to point in the same direction as you did, but it's only going to be 1 unit in length. Notice what I did right here, where I said I wanted to take 1/5 times that vector, or I want to divide all the components by 5. Okay. That process, that thing that we just did, is called scalar multiplication. When we talk about scalar multiplication means we're multiplying by a number. Okay, so we're multiplying by a 2 or a 9 or a 1/5 or a 0.7. We're not multiplying a vector times a vector yet. There are 2 ways of multiplying vectors, and we're not going to do them in this section. Okay. So up above, I have my vector u is -3, -4. Maybe someone says, I need -6 times u. If we take -6 times -3, -4, we just do what we would like to do, what our intuition would tell us. And we're going to multiply the -6 times the x component and -6 times the y component. And what that does is it doesn't change the direction that my vector's moving when I multiply it by a scalar. It just changes its magnitude. So we know that the vector -3, -4 was going in this direction. If we multiply that vector times -6, it's going to go in the same direction. Oh, what am I doing? Same direction, only in reverse. Okay, but now it's going to be 6 times the length as it was before, okay, and pointed in the opposite direction. If I just wanted plain old negative u, -1 times each component, okay, would make that +3, +4. Let's see if I can clone him. Come on. It always puts it in a strange place. Okay, so if that's what u looked like, it's just going to flip it around and have essentially the same direction, but it's going to point in the opposite direction. The initial and terminal sides are going to flip. Okay, so multiplying a vector times a scalar, if it's a negative value, it's going to change, it's going to stay on that same line where it was going earlier. It's just going to go in the opposite direction. And if I take it times a number other than 1, it's going to adjust its length. Okay, taking it times 1/5 is going to make it shorter. Taking it times 6 is going to make it longer. Again, the negative sign points it in the opposite direction. Your author does a good job of drawing pictures of adding vectors. Maybe I should try that in the next video. So maybe I'll give that a shot. I can't promise it'll be pretty, but I'll give it a shot.